Hello, now we are going to start a new video on computer arithmetic for complex networks. In this chapter, we are going to see number representation, right? So this chapter is based on Paham's book. Now course covers up to slide 33, so the book is very extensive, so we are not going to cover all the slides. I do recommend to take a look as further reading in other topics. Residual number system is really a complementary reading. It's very interesting, but you are not going to take a look here, right? So okay, the computer arithmetic, for those guys that like this topic, is a huge topic, you know. We are going to take a look here just in number representation, this topic here, but there are a lot of things about addition, multiplication, division, and all of this stuff, right? So if you would like to build your career in computer arithmetics, probably there is a lot of stuff to do even in the academic science or in the industry, and I'm sure that you are going to see many things very interesting, right? Okay, so these slides, as I told you, they are they they have been got from the Paham's book. Some of the topics we are not going to cover. This is just a control of the revision, and here's the topic that you are going to cover. And the Paham has some sort of humor sense, and I'm not going through this because perhaps it's interesting for Americans, but at least for Brazilian students they don't seem so nice, right? Okay, number and arithmetic. So chapter goals: define scope and provide motivation, and set the framework for the rest of the book. Review position of fixed number. Chapter highlights: what's going inside your calculator, ways of encoding numbers in k bits, radices and digit sets, conventional and the exact forms of representation. So what's the main topic here is what's computer arithmetics. So first of all, probably most of you have heard about the pain-to division bug. Is very well known problem, because in 1994 the company Intel has started to sell many computers using Pentium, and but there is a bug in the hardware. So when they try to make this sort of division here, the correct quotient, it was this first, but what they get is the second. So as you see, it's far away from the precision. It's only 14 bits. And Tom Nice, that's a guy that has discovered this problem. He was doing some problems with twin primes, so it's great problem. As I told you, it's some sort of a slogan, and not so funny for many here, but you can take a look. Perhaps some of you can see as nice. This slide for me is one of most important, because here you can take long time to see many things. Perhaps is one of the slides that Dr. Denis Butusov and me, you can work. We have been working together, because in this slide you can see many interesting stuff, many interesting topics that you can look. So if you are going to work in computer arithmetic, you can focus on hardware or software. In both of them, for example, in hardware, design of efficient digital circuits for primitive and other arithmetic operations, such as plus, minus, multiplication, division, square root, and so on. And issues algorithm, error analysis, speed cost trade-offs, hardware implementation, test verification. You can work in a general purpose and or specific purpose, like digital filtering, image processing, radar tracking, and so on. You can also work on software, numerical method for solving systems of linear equation, partial differential equation, and so on. algorithm, error analysis, computation, complexity, programming, test verification. So most of our courses are going to realize on software, and you are going to work on algorithms, error analysis. So this kind of stuff, it's quite important for many scientific and engineering applications. So this is a motivational example. It's not so good because it's based on an old topic, right? And this is another failure that you can see. It was in a war, the failure of Patriot missile in 1991. So it was a problem in software, not in hardware. So after a couple of hours, there is a truncation in 24 bits. Each truncation has got around 9.5 10 to minus 8 error. After 100 hours operation, they got 0.34 seconds, and the distance traveled by missiles was 507 meters. It's enough to get the wrong goal. Alright, so I will skip this on the top, but if you wish you can take a look with more details. So number and their encodings. So this you can see, for example, some 4-bit number representation formats. The unsigned integer, there is no sign, and signed integer, you use 1 bit to give the sign here, and fixed point, you use some, in this case 3 bits plus 1 bit, so you can use that to, for example, to give 3 bits for integer and 1 bit for fractional part. Sign fraction and complement of 2, and floating point when I use exponent and significant here, and logarithm. So it is quite nice because you can take a look in a very close way the many representation formats, right? So in our next online meet, I'd like to present this discussion here because it's quite nice, and you can use this encoding number here to take a look what happened in assigned integers. So with 4 bits, sign magnitude. So here you have 2 equal numbers for the 0 because you have signed numbers. If you use 3 plus 1 fixed point, so we have this representation, sign fraction. And here's something very interesting, because when I'm using 2 bits for exponent and 2 bits for significant, you have this distribution of numbers here, and the logarithm you have a little bit improved, but it's not so used because it takes a lot of time to make the conversion. So this is what happened here, because you usually have some different representation of numbers. The fixed radix position number is what you usually have in our decimal number, but here it's important that you don't need to think that you are going to use just 0 to 10. In fact, you can represent from minus alpha to beta. So for example, in a ternary number system, the radix is 3, and the digit set can go from minus 1 to 1. So you have minus 1, 0, and 1. You can also have negative radix numbers, for example, from 0 to r minus 1. In this case, for example, you have just 0 and 1 here, right? So more examples of numbers. This is really interesting because, for example, if you have digit set minus 4 to 5 and radix 10, so you can see from minus 4 to 5 you have 10 digits, so that's why the radix is 10. So if you have 3 minus 1, 5, which number you represent? You are going to represent 295. Why? Because this is 3 times 10 to 2 plus minus 1 times 10 plus 5. So 300 minus 10 plus 5 is equal to 295. In a similar way, now using a digital set for a base radix r from equals to 10, you can represent minus 7 to 7, and you have more than one way to represent. So this can be as a redundant way, right? Okay, this is what you are going to see in this video. In the next video, we are going to cover number radix conversion. Okay, I hope that you can enjoy this very short representation number systems. That's going to be useful when you are going to cover more topics about the floating point standard by IEEE. Okay, thanks so much for your attention. See you on the next video.